Hello friends, welcome back to my channel. Today I'll be talking about steady state molecular diffusion of liquid A in stagnant liquid B. This is a case of molecular diffusion in liquids. In my previous video I have started my discussion on molecular diffusion in liquids. I have told how the mathematical expression for Fick's first law can be modified so that you can use it for dealing with molecular diffusion in liquids. Okay, so title for my discussion is I'm continuing my discussion on molecular diffusion in liquids, and then I'll be talking about steady state molecular diffusion of liquid A in stagnant liquid B. Okay, so liquid A, there are again we have a binary liquid solution. The two components are liquid A and liquid B, but the case is, this particular case is liquid B is not diffusing, liquid B is stagnant. Liquid B is not diffusing, it is stagnant, whereas only diffusing component is liquid A. Liquid A is diffusing and liquid B is stagnant. Before we go on and discuss this case, let me tell you why we are discussing this. The reason is, for purely physical separation operations in chemical engineering, purely physical separation operations, purely physical separation operations in chemical engineering. We are talking about operations in chemical engineering. So for purely physical separation operations, two situations are very common. Out of that, this is the first one: steady state diffusion of steady state molecular diffusion of liquid A in stagnant liquid B. The second case, so this is the first case that is very common for purely physical separation operations. Second case that is very common, it is equimolal counter diffusion of liquid A and B. Equimolal counter diffusion of liquids A and B. Okay, so these two situations are very common, and therefore we are discussing those situations. Today I'll be discussing the first one, that is steady state molecular diffusion of liquid A in stagnant liquid B. So at the end of the discussion, we will be getting an equation for calculating molar flux of A, rate of diffusion of A. Okay, similarly, while discussing the second case, we will be getting an equation for calculating Na. Okay, so let us start our discussion. Okay, so let us discuss the case. So we are discussing the case of liquid A diffusing in stagnant liquid B. That is, we are considering steady state molecular diffusion of liquid A in stagnant liquid B. We are going to study molecular diffusion of liquid A in stagnant liquid B under steady state conditions. So what is the meaning of this? Let us understand. At the steady state, molar flux of A is constant. N-type molar flux of A is constant. Constant in the sense it is not changing with respect to time. It is not changing with respect to time. Okay, when this happens, we say that the diffusion is taking place under steady state conditions. So at the steady state, first thing is molar flux of A is constant. It is not changing with respect to time. The second thing that you have to note for this is, when liquid A diffuses in stagnant liquid B, that is when liquid B is stagnant, its molar flux is zero. Its N-type molar flux is zero. When I write NB is equal to 0, it clearly tells us that B is not diffusing. B is not diffusing. B is not diffusing. Not diffusing, the other word for saying this is, that is stagnant. Okay, so Na is constant, Nb is 0 for this particular case. Then molar flux of A relative to a fixed position in space, which is nothing but N type of molar flux. N type of molar flux of A. I have discussed two types, N type and J type molar flux. What are this? I have already discussed in my earlier videos on molecular diffusion. I will give you the links in the description section. I have given links to those videos in the description section. Okay. So what is the equation for this? Again, this has been discussed in those videos. So Na is equal to N into Xa plus Ja. What are the terms involved in this equation? Capital N, it represents the total molar flux. When there are only two components, N will be addition of Na and Nb. You'll come to know about it. So N represents the total molar flux. Xa represents the mole fraction of component A. Whereas Ja, the other type of molar flux, here also you can identify the difference between N type and J type molar fluxes. So Ja represents the molar flux of A relative to the molar velocity of B. Okay. So every term involved in this equation, now it is clear to you. So again, a molar flux of A is equal to total molar flux into mole fraction of A plus molar flux of A relative to molar velocity of B. Okay, let us move ahead. For a binary mixture, since we have considered a binary mixture of A and B, the total molar flux is given as N is equal to Na plus Nb. Total molar flux is addition of molar fluxes of A and B, N type molar fluxes. Okay. For molecular diffusion of liquid A in liquid B, Fick's first law is given by this equation. Again, how this equation is obtained, I have discussed in my previous video. I am giving link to that video in the description section. Okay. So for component A, for the diffusing component, Fick's first law is now written in this way. Ja is equal to minus dab rho upon mw average dxa by dz. To understand the equation, you please watch my previous video. Here, this is the mathematical expression for Fick's first law when it is applied to liquids. Okay, therefore, what do you have? We will use this. We are going to use this expression for Ja in this equation. And if you do that, you have this thing, Na is equal to Na plus Nb into Xa. So in place of N, we have used this equation for N, and in place of Ja, we have used this expression. So Na is equal to Na plus Nb into Xa minus dab into rho upon mw average into dxa by dz. Okay, now let us move on. So with Nb is equal to 0. Why Nb is 0? Because B is stagnant, B is not diffusing. With Nb is equal to 0, if you use it in the previous equation, you get this equation. So what is that equation? Na is equal to Na plus 0, Nb is 0 into Xa minus dab into rho upon mw average dxa by dz. So I have used the condition of Nb is equal to 0. Why Nb is equal to 0? Because liquid B, component liquid B is stagnant. Okay. So in the next step, I have just simplified it. So that is Na is equal to Na into Xa minus dab rho upon mw average dxa by dz. In the next step, what I will do, I will bring this term to this side. So it will be Na minus Na into Xa. So the next step is Na minus Na into Xa, that is equal to minus dAb rho upon mw average dxa by dz. Okay, in the next step what we can do, we can take Na common. On the left hand side you can take Na common. So if you do that, it will be Na into 1 minus Xa, that is equal to minus dAb rho upon mw average dxa by dz. And further, in the next step, I have just rearranged the equation. I have brought this dz to this side, and I have taken 1 minus xa to this side. So you have Na into dz is equal to minus dAb rho upon mw average dxa upon 1 minus xa. Okay. So what can you say about when you after you get this equation? What can you say about this equation? This is a differential equation. So the equation that you have obtained at the end of this step, what can you say about this equation? It is a differential equation that describes how xa is changing with z. So how xa changes with z, you can get it after you solve the differential equation. So this particular equation is a differential equation that describes how xa is changing with z. Okay, the concentration profile of A, if you try to show how concentration of A changes along the diffusion path, you can show it schematically like this. So you have two planes. Let us call the first plane as z is equal to 0. Let us call the other plane as z is equal to z. And then diffusion is taking place from high concentration plane, where mole fraction of A is xa1, to a low concentration plane where its mole fraction is xa2. Okay, so this is the diffusion path. Diffusion path is the distance between these two planes, z is equal to 0 and z is equal to z. Okay, at z is equal to 0, what can you say? Value of xa is xa1, high concentration, and at z is equal to z, what is the value of xa? Xa is xa1. Okay, so this is how concentration of A is going to change as it diffuses from the plane z is equal to 0 to z is equal to z. Okay, now let us move ahead. So from our previous discussion, that is a discussion on our previous slide, uh, what we will do, we are going to integrate the equation. We had got one differential equation, and we knew from the schematic of the concentration profile, we knew the conditions. At z is equal to 0, xa was xa1, and at z is equal to z, xa is xa2. Okay. So over here we have integrated the differential equation. We have used the limits. So it is integration from 0 to z of na dz is equal to integration from xa1 to xa2 minus dAb rho upon mw average dxa upon 1 minus xa. Okay. Now under steady state conditions, now next we are trying to find out the constant terms. So under steady state conditions, Na is constant. It is not changing with respect to time. And if dAb is the average of the best values available at the two ends, if dAb in the equation is itself the average of the best values available for dAb at those at the conditions under consideration. So if that is an average value, average of the best available values at the two ends of the diffusion path, that is dAb at z is equal to 0 and dAb at z is equal to z. If you already have best available values with you, and if dAb represents the average value, then you can consider that as constant. So if dAb is the average of the best values available at the two ends of the diffusion path, dAb is considered to be constant. Okay, so you have the diffusion path z is equal to 0, z is equal to z, and x7, the same profile I have again shown. So over here you know the best value, over here you know the best value, average of this two is DAB, and if that is the case you can consider that as constant. Again I have discussed about it in my previous video. Now the average of rho upon MW average, the average of this this term, which term? Rho upon MW average. Again the average is taken, average of the values at the ends of the diffusion path. That is, you have one value at this end, you have the other value at this end, you take average of those two values, and that average will be considered to be constant. Okay, so let us say that at this end the value of this group is rho upon MW average 1, and at this end the value of the group is rho upon MW average 2. Okay, now we are supposed to consider average of this two as constant. So rho upon MW average is average of these two terms, rho upon MW average 1 plus rho upon MW average 2 divided by 2, that is rho upon MW average, and now we are going to consider this as constant. Okay, so on this slide we have noted that in this equation Na is constant, Dab is constant, and now in place of rho upon MW average we can use rho upon MW average and consider that as constant. So when after identifying all constant terms, next thing that you can do is you can take all those constant terms out of the integral, and that is what I have done in the next. Okay, so from our previous discussion we have this equation Na, it is constant, so we have taken that out of the integral, so it will be Na into integration from 0 to z dz, that is equal to, again these two terms are constant, so they have come out of the integral, so that is equal to minus dab rho upon mw average, average of this is average value, into integration from xa1 to xa2 dxa upon 1 minus xa. Now in the next step we will integrate integration of dz and then integration of d1 upon 1 minus xa. So integration of dz, it is na into z with this limits. We will be applying the limits in the next step. That is equal to minus dab rho upon mw average, average value, and integration of dxa upon 1 minus xa is ln of 1 minus xa, and you have coefficient of minus 1 associated with xa, so you'll have to divide with that coefficient. So integration of dxa upon 1 minus xa is ln of 1 minus xa divided by minus 1, and then of course there are the limits. Limits are from x7 to xa2. So in the next step, what is done, you see, this is negative, this is minus, and there is one more minus sign, so minus minus becomes plus, and you have this step. Therefore Na into z from 0 to z, that is equal to dab rho upon mw average ln of 1 minus xa, from where the limits are from xa1 to xa2. Okay. Now in the next step we will apply the limit. So this is Na into z minus 0 is equal to dab rho upon mw average, average value, and after application of limits you have ln of 1 minus xa2 minus ln of 1 minus xa1. Here there should be xa1. Okay. So after this, in the next step, what we are going to do, what we will do, we will use a logarithmic identity. We know when you have two numbers, say m and n, and if you have this case ln of m minus ln of n, so this is nothing but ln of m upon n. Okay, so ln of 1 minus xa2 minus ln of 1 minus xa1, we will use the logarithmic identity for this term. Okay, so let us do that. So that will be, so from our discussion on the previous slide, you have Na into Z, Z minus 0 is Z, and that is equal to DAB rho upon MW average, the average value ln of 1 minus XA2 divided by 1 minus XA1. I have used the logarithmic identity which I discussed on the previous slide, so you get this equation. Okay. Now, when there are only two components, since this is a binary, you can say solution, where there are liquid A and liquid B, only two components. So for only two components, you have this. So at Z is equal to 0, Z is equal to 0, you have sum of mole fractions will be equal to 1. That is XA1 plus XB1 is equal to 0. Sorry, XA1 plus XB1 is equal to 1 at one end of the diffusion path. At the other end, or from this equation, first let us understand. From this equation, you can write XB1 is equal to 1 minus XA1. So my objective is, in this logarithmic term, I'll be replacing 1 minus XA1 with XB1. Similarly, at the other end, which is that end is at the plane Z is equal to Z, you have XA2 plus XB2 is equal to 1, which gives us XB2 is equal to 1 minus XA2. Okay, so in the next step, we are going to use this in the equation in this equation. Okay, so whatever equation we have got, we are going to use this replacement in that equation. So it will be Na into Z, that is equal to DAB rho upon MW average ln of XB2 upon XB1. Okay, now let us move ahead. Now in the next step, what I am going to do, we will divide and multiply with the driving force. Now for diffusion of component A, in this case, driving force is XA1 minus XA2. And we will divide and multiply uh, on the right hand side. This, you just look at this equation, and then on the right hand side of this equation, we are going to multiply with the driving force. So we are going to do that on the right hand side of the previous equation. Okay, so if we do that, what happens? Let us see. So that will be equal to Na into Z, that is equal to DAB rho upon MW average value ln of XB2 by XB1, and now I have multiplied with the driving force, that is XA1 minus XA2, and at the same time I have divided with the driving force. So let me first erase that so that there is no confusion. Okay, so when you multiply and divide with the driving force, you get this equation. Okay, in the next step, uh, we will see how you can change this form, or how you can rearrange this simple term xa1 minus xa2. xa1 minus xa2 is 1 minus xb1 minus 1 minus xb2. Why? Because xa1, as xb1 is 1 minus xa1, xa1 will be 1 minus xb1. So in place of xa1, we have used 1 minus xb1. Similarly, in place of xa2, we have used 1 minus xb2. Okay. So that means if you simplify it, this will be 1 minus xb1 minus 1 plus xb2, which gives us this xa1 minus xa2 is equal to xb2 minus xb1. So out of the two, if you look at this equation, in the numerator you have this term, and in the denominator also you have this term. Now what I am going to do, I will replace the term in the denominator with the new modification. In place of xa1 minus xa2 in the denominator, I am going to write xb2 minus xb1. Why I am doing this? So that I can properly uh, get an equation for Na. So such an equation which will have driving force in it, so that you can clearly tell molar flux is directly proportional to the driving force. Okay, so let us do it. So what is the task? Task is replace xa1 minus xa2 in the denominator with xb2 minus xb1. Okay, so from the previous slide, from our previous discussion, you have this equation: Na into Z is equal to DAB rho upon MW average ln of xb2 minus xb2 divided by xb1 into xa1 minus xa2, and in the denominator we have replaced xa1 minus xa2 with xb2 minus xb1. Okay, how the replacement is done, I have discussed that on the previous slide. Now let us move ahead. Let us rearrange this equation. Na into Z, that is equal to DAB rho upon MW average ln of xb2 by xb1 divided by xb2 minus xb1 into xa1 minus xa2. So what I have done, I have collected all b terms and grouped that in this bracket. Okay, now just concentrate on the term in the bracket. So what can you say about the term? The term in the bracket is the reciprocal of the logarithmic average of xb2 and xb1. So in order to understand, let us first, we should know how logarithmic average of xb2 and xb1 is given. It is given as the logarithmic average is given by this equation. We are going to denote that by xbm. So xbm is equal to xb2 minus xb1 divided by ln of xb2 by xb1. So if you look at the term in the bracket, you will come to know that it is the reciprocal of xbm. It is the reciprocal of xbm. So we will use that. So from our previous discussion, you have Na into Z is equal to DAB rho upon MW average, and now the term in the bracket is nothing but reciprocal of xbm, so that's why I have this term 1 upon xbm, that is equal to into xa1 minus xa2. So you have Na into Z is equal to DAB into rho upon MW average 1 upon xbm xa1 minus xa2. And in the next step, what I'm doing, I'm taking the Z to the, I'm taking Z on the left hand side to the right hand side. So it will be Na is equal to DABZ upon rho upon MW average 1 upon xbm xa1 minus xa2, and that is the final equation that we wanted. So the equation in this box gives you Na. What is Na? Na, as per this equation, is steady state molar flux of A if it diffuses in stagnant B. When B is not diffusing, only A is diffusing under steady state condition, and if somebody asks you to find out the rate of diffusion, you can directly use this equation. I'm going to discuss numerical based on this in coming videos, you just don't worry. Okay, so above equation, the equation in this rectangular box gives the steady state molar flux of liquid A that diffuses in stagnant liquid B. Okay, so with this I end my discussion for this particular video. My objective was to tell you how you can derive this equation. Those who are doing graduations in chemical engineering, or those who are going to go for great examination, you may get you may be asked to derive this equation, or you may be asked to solve numericals where you will be supposed to use this equation. In any case, this will be useful to us. I hope my today's discussion will help you in deriving this equation. I hope you have learned the derivation. If you have any doubts, you please mention that in the comment section. For today, I'm going to stop. Thank you for being with me. Please subscribe to my channel. Please hit the bell icon. Tell your friends to subscribe to my channel, and hope to see you soon in my next video. In my next video, I'll be talking about the second case. What is the second case? Equimolar counter diffusion of liquid A and liquid B under steady state condition. Okay, so thank you for being with me. Please subscribe to my channel and have a nice day.